Can you keep a math secret? Logarithms are like magic. In the olden days, before computing technology, logarithms helped people evaluate expressions like x equals 9 times the cube root of 2 divided by the 5th root of 7. They would take the log of this expression, call the answer y equals log x equals log of 9 times 2 to the 1/3 power divided by 7 to the 1/5 power, where we have converted taking roots into fractional powers. The subscript 2 is called the base of the logarithm. More will be given about its meaning in a minute. Here comes the part that seems like magic. The logarithm converts multiplication to addition and division to subtraction. How? These are fundamental properties of logarithms that we will strive to explore, understand, and prove. Next, another property of logarithms allows us to convert exponentiation to multiplication. The 1/3 power and the 1/5 power come down in front as factors. At this point, a table of logarithms is used to look up values. Log base 2 of 9 is looked up to be about 3.169925. Log base 2 of 2 is simple, it's just 1. And log base 2 of 7 is looked up to be about 2.807355. We can then use simple arithmetic to find the final answer for y to be 2.941787. Note, however, that we still need to figure out what x is, the original number. Before we do so, let's spend a little time for some explanation. Log base 2 of 2 is 1 because 2 to the 1st power equals 2. Likewise, log base 2 of 9 equals what it does because 2 to the 3.169925 power is about 9. It's similar for log base 2 of 7. Go ahead and take the time to check these numbers with a calculator. But now, how do we find the original number x? We again use a table. To be more precise, we use an antilog and a table of antilogs. Our original number x is the antilog of y, where we found y to be about 2.941787. Looking this up in the table reveals the final answer to be about 7.683626. Of course, we can and should check this with technology. Recall that our original number x is 9 times the cube root of 2, all divided by the 5th root of 7. The cube root of 2 is the same as 2 to the 1/3 power, which is about 1.259921, and the 5th root of 7 is the same as 7 to the 1/5 power, which is about 1.475773. Use your calculator again to get the same final answer, 7.683626. But wait a minute, you say. What in the world is an antilog? X equals antilog base 2 of y turns out to be nothing more than a fancy name for an exponential function, as we learned about in lesson 1.2 of Calculus 1. In fact, it's the exponential function 2 to the y power. Since y, the log base 2 of x, was found to be about 2.941787, you can use your calculator again to confirm the final answer to be about 7.683626. It turns out that exponential functions, i.e. antilogs, are what are called inverse functions of logarithmic functions, and vice versa. And that topic, along with logarithms, forms the core of our content here for lesson 1.4 of Calculus 1. Before we study the properties of logarithms in depth, we should look at some simpler examples. The key thing to remember is that logarithms are defined using exponents, also known as powers. In each case, we have to ask what number to raise the base to get the number inside the parentheses, which is the input for the logarithmic function. For example, log base 2 of 8 equals 3 because 2 to the 3rd power equals 8. This is because, by definition, the symbol log base 2 of 8 represents the unique power to which we can raise the number 2 to get 8, and that number is 3. For our next example, log base 4 of 8 is 3/2. Why? Because 4 to the 3/2 power, by definition, is the square root of 4 to the 3rd power. The square root of 4 is 2, so this is 2 to the 3rd power, and that equals 8. 3/2 is the unique power to raise 4 to in order to get 8. Things get a bit trickier if the input for the logarithmic function is a fraction less than 1. Log base 3 of 1/9 equals -2. Why? Pause the video and think about it. Are you back? The reason is because 3 to the -2 power, by definition, is 1 over 3 to the +2 power, which equals 1/9. -2 is the unique power to raise 3 to in order to get 1/9. Before I show you the next example, you may even want to make up a couple examples on your own. For the next example, I made the base kind of big, but I also related it to the preceding example. log base 27 of 1/9 is negative 2/3. Pause the video to see if you can confirm this. Are you back? Let's double check it now. The reason is because 27 to the negative 2/3 power by definition is 1 over 27 to the positive 2/3 power, which is 1 over the cube root of 27 quantity squared, which is 1 over 3 squared, which is 1/9. Negative 2/3 is the exponent that we are after. Two important classes of examples are when we use base 10 or base e, where e is about 2.71828. We introduced it in lesson 1.2. Again, we think about exponents. Log base 10 of 10,000, which is also just written log of 10,000 because it's a special logarithm called the common logarithm, is ultimately equal to 4 because 10 to the 4th power is 10,000. On the flip side of this, the common logarithm of 0.0001 is negative 4 because 10 to the negative 4 power by definition is 1 over 10 to the positive 4 power, which is 1 over 10,000, which is 1/10,000th. In other words, 0.0001. Log base e also has another name. It's called the natural log. It's also most natural to consider examples where the input to the natural log function involves explicit powers of e itself. For example, log base e of e to the 20th power, written ln of e to the 20th power for natural log, equals 20, and the reason really is completely obvious, because e to the 20 equals e to the 20. Think about that for a second. It really is the reason. Though, if you use the approximate form of e to the 20, which is close to 500 million, it would be a lot less obvious. Our final example involves the natural log function, but the input involves e to a small negative power, which is typical for applications involving exponential decay. Ln of e to the negative 0.05 power equals negative 0.05 because e to the negative 0.05 equals itself. Let's generalize what we've done here. Let's define log base b of x for any positive number b not equal to 1. If you are given a positive number x, log base b of x is the unique real number to which b must be raised to get x. Therefore, by definition, b raised to the log base b of x power equals x for all positive real numbers x. It is important that b is not equal to 1 here, otherwise such a power would not exist when x is not equal to 1. There is a deeper issue to think about, however. Even when the positive number b is not equal to 1, how do you know that such a power exists? Proving that actually requires some pretty in-depth mathematical analysis. However, our task is simpler. Since x is an arbitrary positive number, we can think of log base b of x as a function of x and, for example, we can graph it. Let's look at an example. Let's graph the function y equals f of x equals log base 2 of x for positive values of x. Now, for most functions, it's easier to make graphs by letting inputs continually increase by 1 unit at a time. But for logarithmic functions, as we're about to see, it's easier to let the outputs continually increase by 1 unit at a time. Here's a table of values for the function y equals log base 2 of x. Notice the outputs, the y values, start at negative 4 and go up by 1 unit at a time up to positive 4. What input value of x will give you an output y equals negative 4? It's 1/16. Log base 2 of 1/16 equals negative 4 because 2 to the negative 4 power is 1/16. In a similar way, x equals 1/8 will give you an output y equals negative 3 because 2 to the negative 3 power equals 1/8. One special value to take note of is when y equals 0. The input x equals 1 for any logarithmic function will give you an output of 0 because b to the 0 power will always equal 1 by definition of raising to the 0 power. Make sure you pause the video here and take the time to check the other values as well. Here's a plot of the points we just found. Notice the point in the lower left has coordinates 1/16 comma negative 4, and the point in the upper right has coordinates 16 comma 4. Now connect these dots with a continuous and smooth curve. The graph of this function is always increasing, and it's also concave down. The slope keeps getting smaller and smaller. Don't let that fool you into thinking it has a horizontal asymptote, however. The values of y can get arbitrarily high because we can take the values of x sufficiently big. For example, y can be bigger than 1000 by taking x to be bigger than 2 to the 1000 power. On the left side of the graph, y keeps going down forever and ever as x approaches 0 from the right. This means that the vertical y-axis is a vertical asymptote for this function. Let's describe this limiting behavior symbolically and also be precise in our reasoning. What I'm about to say applies when b is bigger than 1, not when b is between 0 and 1. In this case, the limit as x goes to plus infinity of log base b of x is plus infinity. This is a symbolic way of saying there is no horizontal asymptote as x increases. We are not saying that infinity is a number here. We are saying that the graph of log base b of x will get above any horizontal line, no matter how high it is, as long as x is big enough. Here's the reasoning. This is because, given any positive number m, no matter how big it is, log base b of x will be bigger than that number m when x is bigger than b to the m power. If m is 1,000 and b is 2, x has to be bigger than 2 to the 1,000 power for the output of log base 2 of x to be bigger than 1,000. On the other hand, once again, if b is bigger than 1, then the limit as x goes to 0 from the right, the plus sign means from the right, of log base b of x equals minus infinity. This means the y-axis is a vertical asymptote. The graph will go down forever and ever as x continues to get closer and closer to 0 through positive values. This is because, given any negative number m, no matter how far it is below 0, the log base b of x will be less than m when x is between 0 and b to the m. Keep in mind that b to the m will be a small number when m is negative. If b is between 0 and 1, then different, though related, limiting properties hold. Take the time to figure them out. We are now back to looking at the magic of logarithms. These are the fundamental algebraic properties of logs that help us solve many problems. As always, we start by assuming the base b is positive and not equal to 1. The first property is the one that converts multiplication to addition. The log of a product is the sum of the logs. More formally, log base b of c times x equals log base b of c plus log base b of x for any positive numbers c and x. The next property converts division to subtraction. The log of a quotient is the difference of the logs. More formally, log base b of x divided by c is log base b of x minus log base b of c for all positive numbers x and c. And the last of these properties converts exponentiation to multiplication. The log of x to the c power is c times the log of x. This is true for any positive number x and actually any real number c, positive, negative, or 0. These properties are hard to remember, but they are fundamental if you want to understand and use logarithms. For efficiency's sake, it's worthwhile to take the time to memorize them. Here are some examples to help you believe these properties. These examples can also help you figure the properties out in case you forget them. To start with, log base 2 of 4 times 8 is the same as log base 2 of 32 because 4 times 8 is 32, and that's 5 because 2 to the 5th is 32. On the other hand, log base 2 of 4 plus log base 2 of 8 is 2 plus 3, which is also 5, verifying property 1 for this example. An alternative way to verify this same fact is to use a law of exponents. 4 times 8 is 2 squared times 2 to the 3rd power. Then you can add the exponents to get 2 to the 2 plus 3 power. 2 plus 3 is 5, 2 to the 5th is 32, and of course 4 times 8 does equal 32. The key equality we used was when we added the exponents. Here's a second example for the second property. Log of 10,000 divided by 100 is log of 100 because 10,000 divided by 100 is 100, and that's 2 because 10 squared is 100. At the same time, log of 10,000 minus log of 100 is 4 minus 2 is 2. You get the same thing. An alternative justification is this. 10,000 divided by 100 is 10 to the 4th power divided by 10 to the 2nd power. We can subtract those exponents to get 10 to the 4 minus 2 power, which is 10 to the 2nd power, which is 100. And again, 10,000 divided by 100 is indeed 100. One more example with the natural logarithm will illustrate the third property. Natural log of e to the 4th all raised to the 5th power is natural log of e to the 20th because we multiply the exponents. 4 times 5 is 20. And natural log of e to the 20 is 20 because e to the 20 is e to the 20. 5 times natural log of e to the 4th is ultimately the same thing, 20, because it equals 5 times 4. Natural log of e to the 4th is 4 because e to the 4th equals itself. That really is the reason. An alternative explanation for this is once again based on a property of exponents. E to the 4th all to the 5th power is e to the 4 times 5, and that's e to the 20th. While these examples help you believe and also remember properties of logarithms, they are not rigorous proofs. We will do a rigorous proof of the first property, but first let's do a couple applications. These applications were originally explored in lesson 1.2 of Calculus 1. The first application is to car depreciation. Suppose you buy a new car for $30,000 and that it depreciates in value at a constant relative rate of 18% per year. How long will it take until the value of the car is $5,000? In this case, the value V of the car in dollars is a function of t, time in years, that takes the form of an exponential function, v sub 0 times a to the t. V sub 0 is the initial value and a is the change factor per unit time. Based on the given information, v sub 0 is 30,000 and a is 0.82, giving us this formula. To find how long it will take to reach $5,000 in value, we set the output of this function equal to 5,000 and solve for t. This is tailor-made to use logarithms. While we could take the logarithm of both sides of this equation right away, typically people divide both sides by 30,000 first. Then the equation becomes this: 0.82 to the t equals 5,000 over 30,000, which simplifies to 1/6. To solve for t, take the log of both sides. Does it matter what the base is? Technically, no. However, in calculus, we almost always use the natural logarithm, log base e. E is the nicest base to use for calculus, as we will see. Applying the natural logarithm function to both sides of this equation gives ln of 0.82 to the t power equals ln of 1/6. By the third key algebraic property of logs, the t power can be brought out in front as a factor. And by the second key property of logs, ln of 1/6 is ln of 1 minus ln of 6. Since ln of 1 is 0, this becomes negative ln of 6, giving us this equation. This equation is linear in t and therefore easily solvable. We can just divide both sides by the natural log of 0.82 and cancel it on the left. Our final answer is t equals negative natural log of 6 divided by natural log of 0.82, which is actually a positive number. It's about 9.03 years. This matches the answer we found in a purely graphical way back in lesson 1.2. As another application, consider the doubling time of an exponential growth function. This is a phenomenon that occurs no matter what the starting amount is. The amount of time it takes for the quantity to double is the same, called the doubling time. Again, our situation is exponential growth. The formula for the function is p equals f of t equals p sub 0 times a to the t, where a is bigger than 1. To find the doubling time, set the function output equal to 2 times p0. Then divide out the p0 to get a to the t equals 2. The solution of that equation can be written in two ways, either as log base a of 2, or if you use the natural log to solve for t like we did in the previous example, as ln of 2 divided by ln of a. If, for example, the growth rate is 4% per unit time, so that a equals 1.04, then the doubling time is natural log of 2 divided by the natural log of 1.04, which is about 17.67. Now, to truly test your understanding of logarithms and their properties, you should work at understanding and being able to do proofs of the properties. Proofs are arguments using deductive logic and, in this case, properties of exponents. Let's prove property 1. Log base b of c times x equals log base b of c plus log base b of x for all positive numbers c and x. Start the proof by writing down what you're assuming. We are assuming that c and x are positive. Of course, b is positive as well and not equal to 1. That could be written down too. Besides properties of exponents, all these proofs rely on the definition of a logarithm. In this case, we're using the fact that log base b of c times x is defined to be the number to raise b to get c times x. Similarly for log base b of c and log base b of x. When we make them powers of b, we get c and x individually. Now, look at that expression on the right. Aren't you tempted to add the exponents? You can certainly do so. By a property of exponents, we can do so. We can say that b to the log base b of c times b to the log base b of x equals b to the log base b of c plus log base b of x. Therefore, we now have a chain of equalities that allows us to conclude that b to the log base b of c times x equals b to the log base b of c plus log base b of x. So what we have here is two equal expressions involving b to a power. This means that those powers themselves must be equal. In other words, log base b of c times x equals log base b of c plus log base b of x, exactly what we wanted to prove. Technically speaking, in this last step, we're also using the fact that the function defined by the formula b to the z, where z is an independent variable, is what's called a one-to-one function. That concept will be defined and explored in lesson 1.5. Before ending lesson 1.4 of Calculus 1 by introducing inverse functions, it's worth spending a minute seeing how the identity that we just proved can be interpreted graphically in a special special case in terms of transformations, including something new called a horizontal compression. The identity we will illustrate is this one: log base 2 of 2 times x equals log base 2 of 2 plus log base 2 of x. Since log base 2 of 2 equals 1, this is the same as saying log base 2 of 2x equals log base 2 of x plus 1. We know from lesson 1.3 of Calculus 1 that log base 2 of x plus 1 represents a vertical translation of the graph of log base 2 of x upward by 1 unit. But is there a way to graphically interpret log base 2 of 2 times x? Yes, there is, as something called a horizontal compression. In this visual, we see the graph of log base 2 of x in black get translated up by 1 unit to obtain the graph of log base 2 of x plus 1 in red. Notice that all the vertical red lines have the same length of 1 unit, and the second coordinates of all the red points are 1 more than the second coordinates of the corresponding black points. Amazingly, we can get the exact same final graph if we take the original black graph and compress it toward the y-axis by a factor of 2. All these horizontal blue lines do not have the same length, but the ending points are twice as close to the y-axis as the starting points. Along these horizontal lines, the second coordinates of the black and blue points are the same, but the first coordinates of these points have been cut in half under the compression transformation. The fact that the final red and blue graphs are the same is a visual confirmation of the algebraic identity. We end lesson 1.4 with an introduction to the algebra of inverse functions. A graphical approach to inverse functions will be discussed in lesson 1.5. First, consider logarithmic functions and their defining properties. By definition, we know that b to the log base b of x power equals x for all x greater than 0. Here's a related fact. Log base b of b to the x equals x for all real x. Why? Because x is the power to raise b to get b to the x. Let's relate this to function composition as we learned about in lesson 1.3. If f of x equals b to the x and g of x equals log base b of x, then the definition in red says that f composed g of x equals f of g of x equals b to the log base b of x equals x for all positive x. I'm also labeling this id of x, meaning identity function of x. This is the function that takes an input x and gives you the same number as output. On the other hand, the fact in blue says that g compose f of x equals g of f of x equals log base b of b to the x also equals the output of the identity function, but this time for all real x instead of just positive x. These are symbolic ways of saying that f and g as functions undo each other under function composition. When you compose them in either order, you get a function whose output always equals the input over an appropriate domain. These functions are inverses. For our final example, consider squaring and square rooting. Let f of x equal x squared, and let f inverse of x, that's what that notation signifies, equal square root of x. That's not a -1 power, that's inverse function notation. Then f compose f inverse of x ultimately equals the square root of x quantity squared, which is the identity function evaluated at x for all x greater than or equal to 0. And if you do it the other way around, f inverse compose f of x, you get the square root of x squared, which also equals x when x is greater than or equal to 0. Careful though, if you restrict the domain of f of x equals x squared to only include values of x less than or equal to 0, the inverse function's formula actually changes. In fact, it changes to f inverse of x equals negative square root of x. In the f inverse of x formula, it's understood that x itself is greater than or equal to 0, the square root of x is also greater than or equal to 0, and therefore the output of this function with the negative sign in front is less than or equal to 0, and therefore in the restricted domain of f. When we compute f compose f inverse of x, we ultimately get the negative square root of x quantity squared. That negative sign will go away to give us x, the identity function evaluated at x. Here we are assuming the input is greater than or equal to 0 because that's the domain of f inverse. On the other hand, when we reverse the composition and compute f inverse compose f, we ultimately get negative square root of x squared. This is the trickiest part. The square root of x squared when x is less than or equal to 0 is actually negative x, which is a non-negative number. The two negative signs now cancel, giving us x, which is id of x for all x less than or equal to 0. It's quite tricky. Be careful. Thanks for watching lesson 1.4 of Calculus 1.